Our second speaker for today is Rebecca Chen. She is a Brinson Prize Fellow at Stanford. She completed her PhD in 2025 at Duke University, advised by Professor Dan Skolnick. The title of her talk is Enabling a Photometric Type Ia Supernova cosmology in the Era of Rubin LSST. Rebecca, you can start whenever you are ready.
Okay, thanks. Thanks to the TV for inviting me. Excited to share a little bit of what I work on today. So I wanted to just start with a reminder of what a lot of people I think consider to be two of the most compelling open questions in cosmology today. Remarkably, I've used the same figure as Ikundo to illustrate the Hubble tension. So one of these is the very well-known Hubble tension. And the other one, which has cropped up more recently, is that there have been signals of evidence for an evolving dark energy, which are I think, kind of tantalizing hints at something that could also be cracking lambda CDM. And so, as I've highlighted here in these two circles, Type Ia Supernovae obviously play an important role in both of these measurements. But I wanted to sort of take a little bit of an opportunity to clarify something that I think is a frequent misconception, which is that these are actually separate measurements, right? So while they both use Type Ia Supernovae to infer distances, the measurements of H0 require an anchoring to an absolute distance scale via the distance ladder, for example, whereas when we measure and try and characterize dark energy with Type Ia Supernovae, we can just use relative distances. And that's what I'll be focusing on here. Is I won't touch H0, I'll be just focusing on, in particular, W, the dark energy equation of state parameter, and the power of supernovae to help us try and understand dark energy from this side. Okay, so let me just back up a little bit. So why and how do we use Type Ia Supernovae for cosmology? So Type Ia Supernovae are these particular kinds of explosions, which are these thermonuclear explosions that have roughly the same luminosity. We think we understand their progenitor systems, which is why they have these roughly the same peak luminosity. And because we have this understanding of their luminosities, we can use them as standard candles to then infer distances from them. And we'll frequently emphasize that they are standardizable candles rather than just standard candles, because we know that there are some empirical correlations between the peak brightness of the supernova and various properties of the light curve, like the width of the light curve or the decline rate, which we then have to use to apply empirical corrections to actually obtain our precise distances. So with our supernova light curves, we can get out quite precise distances, and we can then combine each of these distances with redshifts to form what we call a Hubble diagram. And what that lets us do is sort of trace out the expansion history of the universe. And that encodes cosmological information, which then lets us make cosmological constraints on parameters like the matter density, omega m, and in particular, the dark energy equation of state W. So supernovae are this contour in this plane, which are very orthogonal to the CMB. So it's quite, the constraining power is very complementary. Okay. So that seems fairly straightforward, but in reality, the Hubble diagram looks a little bit more like this. So this is the Hubble diagram from the Dark Energy Survey 5-year analysis, which was released last year. And so what I'm showing here is the same thing on the top, just distance versus redshift, where each of these points on here is a supernova. And on the bottom, we're showing the distance residuals, which show the difference between these distances and some cosmological model. And the Dark Energy Survey 5-year sample is sort of the largest and deepest sample collected from a single telescope to date, and is one of the leading measurements that we have from Type Ia Supernovae right now. Okay, so there's sort of a couple components to the analysis that I think are a little bit hidden sometimes. So the first is that is classification. So when we talk about Type Ia Supernovae being standard candles, that means we need to select a sample of supernovae that are purely Type Ias. And you don't want contaminants, what we call contamination, from other types of supernovae, like core collapse supernovae, like types 1bc, type 2. And historically, this has been done using spectroscopy. So if you manage to get a spectrum of the live supernova, then it's a relatively straightforward task to identify the type. You can look for certain spectral features that are present in some types of supernovae and not others. But this is a little difficult because you need to then catch the live supernova in the sky and get its spectrum. And so the DES 5-year analysis was the first to really take this step towards using instead photometric classification. So just using the photometry of the supernova to classify its type, and was the first to use this in a rigorous cosmology analysis. And what enabled this was a lot of hard work and development towards machine learning classifiers that made this a really robust inclusion. And you can see on the Hubble diagram that each one of these points is color-coded by its probability of being a type Ia from these various classifiers. So the dark points are very likely to be 1As, and the lighter points are less likely to be 1As. So you can see there's sort of like a distinct population from these lighter blue points out here that we are successfully sort of identifying as not likely to be type 1As. So I want to emphasize as well that there were a lot of cross checks and tests to make sure that this was a robust thing to do. So on the right here, I'm showing the overall systematic uncertainty budget on W from the 5-year analysis, where each of these different colors is representing sort of different categories of things that contribute to the systematic uncertainty. So things like calibration or the astrophysics of the supernovae. And this green area here are the systematics which are related to photometric classification. And you can see that we're extremely not dominated by classification-related uncertainties, and they're not even actually in the top 5. And what this has allowed us to do is, again, go from smaller samples of spectroscopically confirmed type 1As, so the 3-year analysis had around 200 supernovae, to then being able to use closer to 1,600 supernovae for the photometrically classified 5-year sample. Okay, so I talked about a little bit about the distances and the classification. So what about redshift, this other axis of the Hubble diagram? So similarly, to date, we've also relied on having a spectroscopic redshift from the host galaxy. So for DES, this requires things like having a partner program with OSDES, where we send a list of host galaxies to follow up spectroscopically. Okay, so just to kind of give a sense for where the field is at the moment. So in the next few years, we're having sort of these stage 4 surveys that are coming online that are really going to be revolutionary for measuring dark energy. And so the first of these is the Vera Rubin Observatory, LSST. So the survey should start towards the end of this year. This is a ground-based telescope in the optical. And what Rubin will provide us is really an unprecedented survey area that still has sufficient cadence for transients. So this is completely different from our current mode of operations, where we had sort of smaller deep fields, which we can discover supernovae in. So on the right here is a histogram of the supernovae in these various samples, or the predicted amount in these samples. So in blue here is the 5-year sample, which I showed the Hubble diagram for. And in green here is a simulation of the number of supernovae we expect from LSST. And this is a log scale, so you can see that there's multiple orders of magnitude more supernovae that we expect from LSST. This is really amazing. And the other very exciting avenue is coming from the Roman Space Telescope, which is NASA's next flagship mission, so space-based, observing in the near infrared, and is scheduled to be launched towards the end of next year. And what that will give us is a survey that has Hubble-like resolution, which is really incredible. The field of view is about 100 times what Hubble has. And that will be particularly powerful for helping us observe high redshift supernovae. So in this histogram on the right, Roman is in red, and you can see that it will really push our samples out to much higher redshifts than we've had before from the ground. So both of these are really exciting data sets that are incoming. Okay, So with new data sets comes also new challenges that we have to address. And so namely, one of these is that it's impossible to obtain spectra for every supernova or every host galaxy that we'll observe with these new large samples. So here I'm showing just a table of sort of the different kinds of samples that we've had. So the redshifts have always been spectroscopic, but the classification has sort of, we're now able to use photometric classification rather than just spectroscopic classification. And again, with LSST, our spectroscopic resources can't keep up with the number of supernovae that will be observed. And so what we can consider as a sort of way to address this problem is to make a similar sort of shift from spectroscopy to photometry, where instead of relying on a spectroscopic redshift from the host galaxy or the supernova, we can try to see if we can use a photometric redshift from the host galaxy or supernova. So rather than inferring a very precise redshift, you have to use a coarse sampling from the photometry essentially to infer the redshift. And this area is sort of where a lot of my work has focused on. Okay, so how do we begin looking at this way of doing things? So the dark energy survey is really still an ideal testbed for doing this photometric 1A cosmology with upcoming Rubin. So Rubin, DS is really the direct precursor to Rubin. The filter ranges are similar. Like I mentioned before, though, the survey area is really drastically different. So whereas DES had these deep fields specifically for supernovae, we'll discover transients across the entire footprint of LSST. The number of supernovae is obviously really drastic. And then again, just to highlight the difference in the sort of percentage of spectroscopic resources that we'll have for these two. And then Roman is sort of a different beast, but I included it here in case you're curious. Okay, so the first place we kind of started with this is, so let's start with a subsample where photos are more easily determined than the average galaxy. And so those are red galaxies or luminous red galaxies. Red magic is a particular DES algorithm which selects these kinds of galaxies. And this has the sort of neat advantage of addressing three of the top challenges in supernova cosmology simultaneously. So the first, obviously, is these redshifts are more accurate and precise. The second is classification. So we actually expect really low rates of core-collapse supernovae in these LRGs, which are these red, massive, passive galaxies, whereas the progenitors of core-collapse supernovae, which would contaminate the sample, tend to occur in more star-forming regions. And lastly, we know that there are correlations and open questions surrounding the correlations between supernovae and their environments or their host galaxies. And so we kind of get around that a little bit by having only one host galaxy type for this sample. And then just to give a sense of the numbers for how good these various redshifts are. So host spectroscopic redshift, typically the scatter and uncertainty we expect to be about 10 to the minus 4. A supernova spexy is a little bit worse than that, typically 10 to the minus 3. A typical photo-Z is much, much worse than that. So if you're lucky, you'll get 0.03 to 0.04. And a red magic photo-Z sits kind of nicely in between these, where you do much better than a typical photo-Z, but is obviously not as good as having the spectroscopic redshift. Okay, so then for the DES 5-year sample, of the total sample, about 6% of these of the sample are hosted in these kinds of galaxies. So that's the sample we worked with. Okay, so skipping a lot of the details and the steps. So when we took the light curves all the way to cosmology, we found that using these photometric redshifts in place of the spexy was really promisingly unbiased. So the value in particular that we consider is this delta W value, which is just defined as the difference between the W that you measure when you're using spectroscopic redshifts and the W that you measure when you're using photometric redshifts. So this gives you a sense for the sort of bias that you might expect or the uncertainty that you could then incorporate into your systematic uncertainties. So we found this to be less than 0.01. And on the bottom here, I'm showing the Hubble diagrams for both our data for the spexy and photo-Z, as well as our really detailed catalog level simulations that we did to both validate the analysis as well as correct for sort of known selections in the data as well. And one thing that is that this sort of showed is that as our sample sizes are increasing, one way you can go about things is to actually just selectively choose subsamples such as supernovae in LRGs for cosmology. Okay, so that was really promising to see, but I think the natural question to ask then is, okay, well, how do you go from 6% to 100% of your sample? So can we use other photosy algorithms that maybe don't do as well, but allow us to use all of the galaxies? And so again, we looked at using, we started with the DES 5-year photometrically classified sample, and really took advantage of a lot of the hard work that people have done in the large scale structure community to make really robust PhotoZ. So we took these estimates from the Dark Energy Survey 3-year analysis and tried to encapture sort of a diversity of various PhotoZ algorithms. So each of these is showing a different algorithm, and on the top is the PhotoZ compared to the SpecZ. So this one-to-one line, if everything fell on this line, then that would mean your PhotoZ are absolutely perfect. And on the bottom, I'm showing the bias and scatter of these for these various algorithms. So the blue one here is the scatter, which was that number that I quoted earlier. And so there's some range. So one of them or two of them are machine learning based, but one is more calibrated specifically for tomographic redshift bins. But this one is template based. So we're trying to get a range of the diversity in algorithms. Okay, so one other thing we can do is we can actually use information from the supernova light curve itself to help constrain the redshift. So this is kind of intuitive because you have a time series of photometry, so there's some color information in there. There's obviously information that we can use to help make this constraint. And so typically when you do your light curve fit, you have your light curve, your photometry, and you give it a specific redshift, and that lets you fit your peak brightness and various standardization parameters. But instead of doing that, you can let the redshift float in your fit and give it a prior that comes from the host galaxy photometric redshift. And so that gives out the same peak brightness and standardization parameters after your light curve fit, but you also now have a supernova plus host photometric redshift. And this is the approach that we took. So this is the same sort of plot that I just showed where you have the PhotoZ versus the SpecZ, and in each of these cases is sort of a different variant of PhotoZ. So the supernova plus some different prior coming from the host galaxy. And what I kind of want to show here is that the supernova information is helping reduce the PhotoZ scatter by about 50%. So on the bottom, these orange lines are showing the scatter from when you just have the host galaxy information. And then the blue line is showing the scatter from when you have the supernova plus host. So in most of these cases, that information is helping a lot. Okay, and then jumping all the way to the end, again, to the cosmology, this is one of the Hubble diagrams for a specific PhotoZ case for the data. And on the right here is sort of the money plot of that paper, which is showing the delta W values again for various cases of using different PhotoZ. So a delta W value of 0, which would mean you're getting exactly the same thing with SpecZ and PhotoZ. And each of these is a different algorithm. In blue here are the results from data, and then in black are simulations with including both core collapse supernovae and type Ias. So that requires you to then do a full treatment of the photometric classification as well, which I mentioned before. And then in pink is if you do your simulations just with 1As. So what we're happy to see is that the difference between the black and the pink is quite small. So that means that the contribution to your systematic uncertainty from classification is very minimal and not dominant. And so for some of these algorithms, we were able to measure unbiased W within our overall W uncertainty of about 0.04. I just wanted to emphasize again that supernova cosmology is really rapidly entering this really exciting and unprecedented new era of data. So LSST's data preview 1 is out now. Survey should start end of next year, beginning of next year. Rome is on track for launch. Again, these telescopes have immense potential, but obviously we need to also overcome some of these new challenges like the lack of spectroscopy.
Thank you, Rebecca.